Welcome my friends, welcome to my next lecture. So now in my last lecture I talked about the statement of what is called Stokes theorem, and one example I was talking about, but there was some issues with the normal vector. So I will clarify today's lectures, and then I will talk about one more example on Stokes theorem, and then I will move my discussions to what is called Gauss or divergence theorem. So that's my plan. Again I will talk about some more examples on Gauss divergence theorem, and that will complete the kind of these sections. So let me start with the statement of Stokes theorem once again, and the example I was having difficulties little bit regarding the unit normal vector. So I will clarify that one, and then I will go for one more example concerning Stokes theorem, and then I will move our discussion to what is called Gauss divergence theorem. Yeah, so as I said, so let me just recall the what is the meaning kind of statement of Stokes theorem. That is nothing but the three-dimensional what is called Green's theorem I already discussed. So what is that? Once again I just recall. So this is the corresponding surfaces I have given, and you have the natural orientations of the surfaces is given, and that will induce our orientations of the boundary, right? That means a positive orientation, if you know, right? So that means what? Let me start with your surface with some orientations, then it will induce a positive orientation on the boundary. That means if I go in such a directions on the boundary of the surfaces, so that if I see my surfaces always in the left hand side, if that is the case, then you will have the positive orientation. Now look at the surfaces. So another way, so you have a surface, you have a kind of say positive orientations of the surfaces. That means the unit normal is the pointing upward directions. Now if I use the what is called right hand thumb rule, that means you put your directions of thumb along the direction of the what is called your unit normal pointing upward, then the corresponding curling finger, it will give you the directions of the boundary. Like for example this picture, see, if this is the corresponding unit normal, thumb is in that directions, so therefore the corresponding directions of the curve, which is nothing but what is called anti-clockwise or counterclockwise direction. So that means this is the directions. This is the direction, means if I move in this way, that means my surface is always in the left hand side. Okay, so if I have that kind of notion, surfaces and the corresponding directions or oriented surfaces boundary, then the corresponding Stokes theorem says that let S be a smooth surface oriented by its positive normal. That means you start with a surface comma plus n cap. Assume that your surface S is bounded by a closed piecewise smooth curve C, whose positive orientation is induced by the orientations of S. So you have a orientations of your smooth surfaces which will induce a positive orientation of the boundary. Once I have that one, then you start with a vector field capital F, whose component is M, N and P. It is a continuously differentiable vector field. That means it is differentiable and derivative is also continuous. Then the corresponding statement of the Stokes theorem says the corresponding vector line integral of your vector field capital F over C, which is nothing but m dx plus n dy plus p dz over C, which exactly equal to the corresponding surface integral. What is the surface integral? Surface integral of this object. That means you have to calculate the curl of F dot n cap. That means you are taking the normal component of the curl and you perform the what is called the scalar surface integral of this integrand, this one. Okay, so this kind of surface integral is exactly equal to the what is called line integral or vector line integral. So that is a statement of the Stokes theorem. Then in my next example I was talking about verifying Stokes theorem if I have this vector field and this surface is given. So now what is there in the problem? So look, so I am starting with my vector field capital F, whose component is 2z, 3x and 5y, right? And you see this is a functions of x, y, z. So this is very nice. This is continuously differentiable vector field. And what is my surface S? S is the portions of my paraboloid z is equal to 4 minus x square minus y square, where z is positive with normal pointing outward, right? Then I am saying that okay, then verify the Stokes theorem. So therefore, if I just look at the boundary curve of my surface, which is nothing but the circle x square plus y square is equal to 4, because if you put z is equal to 0, that means take the projections in the xy plane. Okay. And with the orientation is counterclockwise directions, which is the positive orientation induced by orientations of my surfaces. So once I have that one, then I am saying that okay, verify your Stokes theorem. That means in the left hand side whether the left hand side is exactly equal to the right hand side. The left hand side is nothing but the what is called line integral of my vector field capital F over C, and the right hand side is the surface integral. So let's first calculate the what is called line integral. So that means if I know if I just write my what is called curve as a parameterizations, which is a circle x square plus y square is equal to 4. So therefore if I will have 2 cosine t, 2 sin t times 0 times k cap, this is the corresponding what is called parameterizations of my curve C, boundary curve C. Then if I calculate the corresponding what is called vector line integral of my vector field capital F, which is nothing but m dx plus n dy plus p dz, and it is very easy because you have the parameterization. So this is nothing but 0 to 2 pi. So this z, which is nothing but here actually there is no one kind of component of 2z dx, right. So let's see. So that means my z is look here. So if what is my parameterization? That means this is my x 2 cosine t, 2 sin t, z is 0. So therefore it will not contribute anything. So second one is should be 3x. What is my x? So x is nothing but 2 sin t. So that means 3 times 2 sin t means 6 cosine t, and dy, y means again 2 cosine t. So 2 cosine t, and would be dt. And what about the third one? So dz, then again it will not contribute because z is component is 0, so therefore this is 0. Okay. So that's kind of integration you have to perform, and if you do that it will end up with t from 0 to 2 pi 12 cos square t, and if you do that integrations you will end up with the value is nothing but the 12 times pi. So therefore the left hand side value of the line integral of my vector field capital F over the boundary curve of my surfaces S is 12 pi. Now let me see whether this is exactly equal to the surface integral in the right hand side. So there I was having little of doubt. So what is the surface integral there? So this is the one you have to calculate, right? You have to calculate curl. Then you have to take the normal component of the curl, that means take the dot product with n cap, and then you have to perform the surface integral. Now there should not be any confusion. Second, why? Because if you see the when I talked about I think my couple of lectures before, when I talked about the surface integral, if you remember, if I have a surface, so what is my surfaces here? This is my surfaces, right? So this is given, this is the explicit form, z is equal to 4 minus x square minus y square with z is positive. That means the surfaces you will have parameterizations. Now if I have a surface which has explicit form is given, then it will have a parameterization automatic. What is that? So you can have phi of xy, which is nothing but x comma y comma, and then what is that? This is g of xy. And what is my g of xy? This is explicit representation of my surfaces. Then x comma y comma, this is 4 minus x square minus y square, right? So that should be the case, right? Then once I have these parameterizations of my surfaces S of this one, then this surface integral, if you remember, it will boils down. So this is my parameterizations of my surfaces, where x, y, what is the region in the two-dimensional setting? This is x square plus y square, I think, which is lesser equal to 4, right? Or the region, R region, right? So this is the x, so this is the 1. So this is in R, which is nothing but the circle. So therefore, what is the kind of corresponding formula if you remember? So this is nothing but over the integral over the region R, and then what will happen, you will have, suppose I want to, okay, maybe I think I just remove that one. So let me just go back. So first let's see what is the parameterizations of the given surfaces is given. Okay, so for example, look this one, I already discussed that one. Yeah, so if suppose surface is defined by the equations z is equal to g of xy, that is given like z is equal to 4 minus x square minus y square. So that means it is of the explicit form. Once I have that, then your surfaces is nothing but collections of all xy z, or xy runs over r and z is equal to gxy, right? So now that r you know, right? That r is nothing but my circle, right? And what is my z? This is 4 minus x square plus y square. So therefore the corresponding parameterization is phi xy, which is x comma y gxy. So then you have to calculate the unit normal vector, which is of this kind of form. Then the corresponding surface integral, actually you can write it, the surface integral you can, suppose if I want to perform this surface integral, right? Yeah, so if I want to perform this surface integral, so that means if I write it, this is S, say I have a surface integral, say suppose I have a vector field F, so then you have something, then the sigma, okay, so maybe I think I should write, so I should not. Okay. So what I am trying to say is that suppose you have some surface and suppose you have some vector field dot n cap d sigma. Now when I discuss that what is called surfaces integral, and suppose your S is nothing but phi of r. Okay, so this phi is the parameterization. Here you can have the parameterization because your or what is called this surfaces is very nice. It is given in the explicit form. And what is this? This is exactly x comma y comma gxy. So this exactly equal to, if you write this is exactly equal to integrations over r, then you can have phi of capital F of phi of x comma y. Then what will happen? N cap. So n cap means what? That means phi x cross phi y divided by phi x cross phi y, okay, uninormal vector. Then you will have what will have, then you will have this is again to the double integral, that means here you will have another norm factor will be there, phi x cross phi y times dx dy or du dv, it depends which variable you are talking. So now do you see this factor will get cancelled. So therefore it is exactly equal to your integrations over r f of phi of xy, okay, times phi x cross phi y, this is a dot product, right, times dx dy. And this is exactly the formula I am actually talking about here itself. So therefore that normalization factor that in my last class I was bit confused that it should be, but it actually get cancelled if I changed my surface integral to the corresponding parametric form. If I have a surface whose parametric representation is given by this phi, where this surface is given in the explicit form, therefore you can directly use this formula. I mean your this surface integral, it boils down to this double integral over this object f of phi of x comma y dot phi x cross phi y and then dx dy. So that's what is actually. So there should not be, I mean you just calculate the phi x cross phi y. Now what is my phi x cross phi y? This is nothing but minus gx minus gy comma 1. That's, you can see what is phi x cross phi y. You'll see phi x cross phi y, you just check it. You see phi x cross phi y, you see minus gx minus gy then 1. That means you just forget about this normalization factor. It actually get cancelled with the d sigma if I write it phi x cross phi y times dx dy. So that normalization norm factor will get cancelled. So you'll end up with just the vector field, then acting on phi of xy, that parameterizations, then dot product with phi x cross phi y. That is why there should not be any normalization kind of norm factor will be there. So therefore you have to just calculate this object. So I think now it's clear. Okay. Yeah, so that is why, so this is nothing but you just calculate the curl, okay, that this is my curl, this is, you can easily calculate it by the determinant formula I already told you, this is I cap, j cap, k cap, then you have to have del del x, del del y and del del z, okay, and what is your f? F is nothing but 2z 3x 5y, so therefore you can 2z 3x 5y. If you just find the determinant formula, you will end up with this one. N cap, which is nothing but this time as I said, it's this n cap is actually I am talking about, actually this is phi x cross phi y. I should write this is not the normalized one. So this is actually, you can write phi x cross phi y. It is not n cap. I mean if you think about n cap as the normalized one, so that means this is not exactly this one, this is actually phi x cross phi y. Because n cap means if you think about it, okay, n cap means unit normal vector, then I have to always divide by norm. But here actually I am talking about n cap means phi x cross phi y, because in the integrations it will not affect because it is over the region R that I know, and this is nothing but this is actually f of phi of xy, which is nothing but this object, and then dot product with phi x cross phi y, and which is nothing but this one, which is this one. Okay, so therefore you have to perform this actually double integral, and this region is perfectly all right, you know, the circular region. So therefore you just take the parameterizations of your circular region. So therefore this is nothing but r from 0 to 2, theta from 0 to 2 pi. So therefore what will happen, this should be x is equal to r cosine theta, y is equal to r sin theta. So then what will happen? So therefore this is r dr d theta, and if you calculate it, it will end up with 12 pi. Okay. So I think it is clear. So there should not be any confusions here. So therefore just you need to have the parameterizations of my surfaces. Since my surface is given in the explicit form, so the corresponding parameterizations of my surfaces is nothing but phi of xy, this where xy varies over the what is called region in the xy plane, x square plus y square less or equal to 4. That means this circular, the region in the xy plane is nothing but x square plus y square less or equal to 4. So I can say that R is nothing but all those xy in R2, okay, so such that x square plus y square is less or equal to 4. So this is the region. So if I take a phi map from this region to R3 and whose components are x comma y comma z, z is equal to 4 minus x square minus y square. So once I have that one, then the corresponding surface integral you can easily write over the region R. Then what will happen? Then you just calculate that curl of f, this is a vector field acting on phi of xy, okay, dot product with phi x cross phi y, and then dx dy. So that's the formula I am using. So that means you do not need the normal. So n cap, that will get cancelled. So that n cap is nothing but what? As I said again, n cap is nothing but phi x cross phi y divided by norm of phi x cross phi y. And this d sigma will produce one more norm. So that means this is nothing but again norm of phi x cross phi y times dx dy. Okay, and this get cancelled. So you will just end up with this phi x cross phi y. So that means you just consider this vector field curl of A. So acting on this parameterization phi of xy, which will give you this vector 5 cap 2j cap plus 3k cap, and then you have to dot product with phi s cross phi y, and which is nothing but this one. So maybe you can bit confused with the n cap, but this n cap actually I am talking about this phi x cross phi y. And then you just perform this what is called double integral. Since your region is very nice region, circular region, that means it is the region bounded by your circle x square plus y square is equal to 4. So therefore you just take the polar representation, that means r prime from 0 to 2, theta from 0 to 2 pi, and x is equal to r cosine theta, y is equal to r sine theta. So you'll end up with this one. Of course that area 1, so that means if I change it to polar coordinates, so that means dx dy should be replaced by r times dr d theta, if you remember. So therefore you have r dr d theta, and this is a very simple integrations. You just calculate it, you will end up with that. This is exactly equal to 12 of pi. So therefore the left hand side is exactly equal to the right hand side. Okay, so therefore I think there should not be any confusion, and it is clear. So this is perfectly all right. So that you just go back to the what is called, when I was talking about the notions of what is called vector surface integral or scalar surface integral, there it is there, that how you can change it to the corresponding. If I have a surface, if it has a parameterization from phi of uv, you can have this surface representation in terms of parameterizations, then you can have the surface integral in terms of parameterization. So it actually follows from there. Okay. And this example I already talked about. So just you have to calculate this what is called this surface integral. So again you just use what is called Stokes theorem. This surface integral exactly equal to your what is called line integral of this kind of object. So this is by what is called Stokes theorem. So here it is your vector field. It is very nice, and here S is the upper hemisphere in the upper plane. So that means x square plus y square z is equal to 1 with unit normal vector pointing upward. So therefore if I just want to calculate this surface integral by Stokes theorem, which is nothing but this what is called line integral of this capital F, and what is my c? So that means this is x square plus y square is equal to 1, that means projections in the xy plane. Okay, so again in the directions will be counterclockwise. So now it's a circle. So again I just already discussed. So what is the parameterization of c? This should be a cosine t comma sine t and then comma 0, right, because it's a circle of unit radius and t runs from 0 to 2 pi. Okay, and then if you perform this line integral, what is this? This is 0 to 2 pi f of what is called this if I write it as rt parameterizations. So f of rt, then r prime t dt, right, dot product. You just calculate f of rt. What is f of rt? So you can write f of rt, which is nothing but f of, so cosine t comma sine t comma 0, which is nothing but what will happen. So this should be y square, that means it should be sine square t, then x comma 1, then sine t comma cosine t, and then you will have 0, right. This is f of rt. And what is r prime t? This is your rt parameterizations, right. And what is r prime t? So you can easily calculate r prime t. This is nothing but minus sine t, then cosine t comma 0. Then you have to take the dot product. So therefore f of rt dot product with r prime t, what it will give? It will give you actually, so you will have sine square t. Again I already discussed this one, again just I am quickly discussing this part. Dot product with minus sine t cosine t 0, what it will give? So that means this should be minus sine q t plus sine t cos square t, right, because the third one will not contribute anything. And what is this? This is nothing but, if I just take common sine t, this is cos square t minus sine square t. So that means you have to perform this integration 0 to 2 pi. Okay, so sine t, and then what is this? The cos square t minus sine square t dt. Okay, and what is this? This is a trigonometric formula you have to use, right? 0 to 2 pi, then sine t, then I think if you, what is the formula? Cos square t minus sine square t, I think it is cosine of 2t, I think. You just check it, okay, it is very easy. Then again you have to use the formula sine a cos b, sine of a plus b by 2 plus sine of a minus b by 2. So what will happen if you just use the trigonometric or this formula, trigonometric formula. So finally you will end up with this kind of integration 0 to 2 pi of some sine function or some cosine functions. Okay, but since I am integrating over the full circle 0 to 2 pi, so you will actually end up with a 0. You will get 0. Okay, please complete the full solutions I just said. So the idea is that you have your vector field capital F, you have your parameterizations, you just perform this what is called line integral. And what is the formula? You know, once I have the parameterizations R, so therefore you have to just calculate f of RT dot product with R prime t dt. And as I said, if you just calculate f of RT dot product with R prime t, it will involve R trigonometric functions, either sine functions or cosine functions. Now if I integrate over full circle like 0 to 2 pi, it will give you 0. So therefore if I calculate it expressly, you should please do that in details. I have just given you that what's called the idea or some steps I just discussed, but you please complete it. You will see that this what is called this line integral, this is 0, and therefore by Stokes theorem it is exactly equal to this one. So therefore you will end up with this surface integral of this object is 0. So sometimes it will be useful, right? So like for example, if I give some vector field some surfaces, and if I say that calculate this kind of surface integral, and if it satisfies all the hypotheses of surface integral, then you use Stokes theorem, you calculate this line integral, and the value of the line integral will be the what is called your required surface integral. Okay, so this is another example. Okay, so now I should discuss what is called the kind of Stokes theorem. So earlier one, I will have a surface, nice surfaces, smooth surfaces with some positive orientation. That means that you have a unit normal vector pointing upward. Now this time I want to discuss the Stokes theorem. If we have a surface, but this time surface contains couple of holes or finitely many holes. Okay, so look, so this is the picture. So that's why I am written extending Stokes theorem to surfaces with holes. What is that? So Stokes theorem can be extended to a surface with finitely many holes in the same manner of extending Green's theorem to multiply connected domain. If you remember, when I talked about Green's theorem, I have given two statements. One is Green's theorem for simply connected domain, another is Green's theorem for multiply connected domain, right? If you remember that one. So similarly, since it is Stokes theorem is nothing but the three-dimensional version of Green's theorem, so therefore I can start with the surfaces with say finitely many holes. What will be the corresponding statement of what is called Green's theorem in the 3 dimension, or this is nothing but the statement of Stokes theorem for a surfaces having finitely many holes. Okay. So this kind of surfaces you already seen in my last lecture I talked about. So this is a surface, this is the corresponding boundary, but it has another two boundaries. This is the outer boundary C, inner boundary C1, C2, because these are the hole. So this white portion is not in the part of the surfaces. Okay. So this kind of surface I already talked about. Suppose you have a given this kind of surface with positive orientation, that means your at point normal pointing upward, then these orientations will automatically induce what is called positive orientation on the outer boundary, which is C. That means if I move in the counterclockwise directions, my surface is in the left hand side, there is the positive orientations. On the other hand, if I look at the inner boundary, that means C1, C2, so the corresponding surface will induce a positive orientation on the inner boundary C1, C2 if I go along C1 in the clockwise direction. So because if I go in this direction, then my surface is in the left hand side. Similarly, if I go in this direction, my surface is in the left hand side. So therefore, the given what is called orientations of my surfaces, if I start with the orientation smooth surfaces with some orientation, that will induce orientations in my boundary. So this kind of surfaces in the outer boundary, it is the what is called counterclockwise directions, and in the inner boundary C1, C2, it is given the clockwise directions. Once I have this kind of surfaces, then note that the orientations of the inner boundaries C1 and C2 of the inside holes. Okay, orientations of inner. So this is actually clockwise orientations. Once I have this kind of surfaces, okay, once I have this kind of surfaces, then what is the corresponding statement of Stokes theorem? It says that the corresponding line integral of my vector field capital F, then you have to add. So I k from 1 up, so I have two holes, so therefore it is the corresponding what is called vector line integral of my vector field over Ck, and if I add it, then it will give you the corresponding surface integral of this curl of F dot n cap. So that means this is nothing but the normal component of my curl. So now you may ask then one question here, that if you just connect with the what is called the Green's theorem, right? If you remember the Green's theorem for the multiply connected domain, if you look at the statement, the exact statement will be there in the two-dimensional setting, but you see there was a minus sign here. There was a minus sign. Then you may ask why the minus sign you have removed and make it to a plus sign, and it is automatic, because you see, if you remember there in the multiply connected domain, when I was talking about Green's theorem in the two-dimensional setting, there you will have a domain something like that, and you have a hole there. So the orientations of the boundary curve, outer boundary, which is same as the inner boundary, then inner holes like this is C1 and C2, right, and this is the outer one. So that means this is in the counterclockwise and anticlockwise, and both of the inner curve C1, C2, that is also kind of anticlockwise. So therefore there was a minus sign. But whereas now if I look at the surfaces here, outer boundary will have the counterclockwise, means positive directions. However, to have the positive direction induced from the surfaces, the corresponding directions of C1 and C2, that means inner boundaries will be in the clockwise direction. That is why this negative sign replaced by the positive signs. That is why. So that means since C1, C2 are in the clockwise directions, so therefore that minus sign earlier one whatever. Earlier means the Green's theorem when I was talking about in 2 dimension, that is in the anti-clockwise direction or counterclockwise direction. That is why the minus sign was there. But now this time what I am having the positive orientations of my inner boundary C1, C2, which is actually clockwise direction. That is why the minus signs in the statement there, it should be replaced by plus sign here, because now this time I have the orientation in the clockwise direction. That is why there was a minus sign there, because I am having this anti-clockwise or counterclockwise direction, but this time I am having clockwise directions. So therefore that minus sign should be replaced by plus signs, and therefore the left hand side is exactly equal to the surface integral of this object. That means you consider the curl of the vector field, take the normal component and perform the surface integral. So this is the statement of Stokes theorem if I have a surfaces with finitely many holes. This is 2 holes, that is why it's from k from 1 to 2, but if I take finitely many, it will run from k from 1 to n. Okay, so if I have a finitely many holes, so that means the corresponding statement of the Stokes theorem if I have a surface with finitely many holes. Okay, so I think the statements of Stokes theorem is clear. So I have stated the Stokes theorem for a nice surfaces first, and then I stated the Stokes theorem for surfaces with finitely many holes. Couple of examples I have discussed. Okay, so this is applications of Stokes theorem. What is application? So you can see that using Stokes theorem, one can show that any irrotational vector field is conservative. Okay, so that means what is irrotational vector field? That means if my curl of my vector field should be 0. So if the curl of the vector field is 0, then one can prove that it is conservative. Because why? Because you see, look at the Stokes theorem. Stokes theorem, it says that if I have a nice surfaces, then Stokes theorem says that the corresponding line integral, this one is exactly equal to the corresponding surface integral of this object, curl of f dot n curve. Now if I start with a irrotational vector field, then its curl is 0, so therefore the right hand side is 0. Right. So therefore the left hand side also should be 0. Now what is called conservative vector field? If I have a vector field and if I have a region, it is conservative means if I take any simple closed precise smooth contour or curve inside my kind of domain, then the vector line integral over this simple closed piecewise smooth contour should be 0. Right. Now Stokes theorem, it's exactly this one. So Stokes theorem says that this is the connections between the what is called line integral over any boundary of the surfaces is exactly equal to surface integral of this object. Now if I want to prove that, if I start with a irrotational vector field, then curl f of should be 0, right? And then if I start with a domain and if I take a kind of simple closed piecewise smooth closed contour, and if I consider the surfaces bounded by that one, then in the right hand side, since it is irrotational vector field, that means curl f is 0, so therefore this is exactly equal to 0, and therefore it will implies the corresponding what is called line integral over any simple closed piecewise smooth contour C is 0, and this is nothing but the conservative vector field. Okay, so that is one of the applications. Another one, it says that using Stokes theorem we can obtain an alternative form of the Ampere's law. That means what? That means the total flux of electric current flowing through a loop is proportional to the line integral of the magnetic field around that loop. Well, that is the kind of thing. That is the right hand side is the surface integral. That means I am talking about the total flux. Total flux of electric current following through a loop is proportional to the line integral, because the Stokes theorem connects between the line integral and the surface integral. So it's to the line integral of the magnetic field around the loop. So this is like the gradient cross B, which is exactly equal to mu naught J, that does not involve any integrals. Okay, so this is 2 applications of what is called Stokes theorem. Okay, so I think so this is all about Stokes theorem. So I have started with surfaces, smooth surfaces, then orientations of the surfaces I have discussed. Then I talked about the statement of Stokes theorem for nice surfaces, that means the surfaces with no holes, and then couple of examples I have discussed, and then I gave the statement of the Stokes theorem if my surfaces has finitely many holes, and the applications I just said using Stokes theorem you can conclude that irrotational vector field is conservative, or you can using Stokes theorem, using Stokes theorem, you can calculate the total flux of electric current involving through a loop is proportional to the line integral of the magnetic field around that loop. Okay. So there are many kind of applications, so I have just discussed 2 here. Okay. So now I think I should move forward. Now next concept is to talk about what is called Gauss theorem or divergence theorem. So like the Stokes theorem, I said that it is nothing but the 3-dimensional versions of the Green's theorem. So what is Gauss divergence theorem? This is nothing but the analogous of divergence or normal form of Green's. So now if you just reconnect or recall your Green's theorem, there was a tangential form and the normal form. So there actually I am talking about divergence theorem means it is the normal form of your Green's theorem. When you will see the statement, then it will be clear. So it is analogous to the divergence of normal form of the Green's theorem. So let's see what is the statement of Gauss divergence theorem. Okay. So this is the statement of Gauss theorem or Gauss divergence theorem. What is that? Yes. So what you have to do, you start with a solid region in the 3-dimensional Euclidean space whose surface S is oriented by its positive normals. Okay. So that means you start with a solid region in R3 and it will have a surface S. Suppose it is oriented positively, that means I am talking about the region, solid region S, and the surfaces you will have a positive, that means the normal you will have, it is pointing outward. Okay. And then you start with a vector field capital F, a nice vector field, that means it will have a components capital M, capital N and P. It is continuously differentiable, that means if I start with a very nice vector field, that means it is differentiable, derivative is continuous. Vector field on some open set containing your solid region G. Then it says that the corresponding surface integral, that means that you just take the normal component of your vector field and perform the surface integral. This is exactly equal to the corresponding what is called triple integral. That means the triple integral over the solid region G of the divergence of F. So that is why it is called the divergence theorem. Okay. So therefore it connects with the surface integral and equal to the volume. Again, you just see that is also kind of fundamental theorem you will see, because you have a solid region right in R3. So therefore, and then what I am doing is that, or divergence theorem, or it says that the integrations inside, that means in the solid region, it exactly equal to the integrations over the kind of 1 dimension less, that means on the surface. So that means somehow I am talking about the fundamental theorem, that means I am reducing, that means the kind of like fundamental theorem like A to B, A prime x dx, which is nothing but a b minus a, that means integrations from 1 dimension reduced to the 0 dimension, that's value of the point. Similarly here also similar thing going on. So I want to, I have integrations over the solid region, somehow I am just reducing to 1 dimension less, that means I am going to the surfaces. So that is, you can think about in this way, that is actually called the Gauss divergence theorem. So that means if I have a solid region and suppose you have the corresponding surfaces oriented positively, positive normals, and if I have a vector field which is very nice, that means continuously differentiable vector field, then the corresponding surface integral of this f dot n cup, that means the normal component of the vector field I am talking about, this surface integral exactly equal to the what is called triple integral, where integrand is divergence of f. Okay, so one example let me just discuss. So just to verify the Gauss divergence theorem, look what I have given. So use the Gauss theorem or Gauss divergence theorem, whatever it is, to find the outward flux of the vector field, this capital F, across the sphere. Now what is that outward flux? Then if you remember when I was talking about surface integral, scalar surfaces or vector surface integral, if you remember this kind of object I talked about, and this is nothing but the what is called flux of my vector field F. So that's part was, I already discussed this kind of notions there. So that is why, so I am asking found the outward flux of my vector field. That means you have to perform this surface integral. That means you have to have the surface, you perform this, you take the normal component of your vector field and you perform the surface integral, and the value is nothing but the what is called outward flux of my vector field across the sphere, because this surfaces is nothing but x square plus z square is equal to a square. So that means if I say that, okay, calculate the outward flux of the given vector field capital A across the sphere, that means you have to perform this kind of surface integral. But what Gauss divergence theorem says, this is nothing but the corresponding triple integral. That means you look at the region, solid region bounded by the surfaces given, if this is G, that means you just perform this what is called triple integral. That means you calculate the vector, you have the vector field, you calculate the divergence, you get the region bounded by your surfaces and perform this triple integral. This value is exactly equal to the surface integral of this one, and which is nothing but your what is called outward flux of your vector field across your sphere x square plus z y square plus z square is equal to x square. Okay. So therefore I say that use the Gauss theorem to find the outward flux of the vector field F across the sphere. This one, that means I have to perform these integrations. Since I have to use Gauss theorem, which is nothing but exactly equal to this triple integral, that means you just look at the solid region bounded by the surfaces, which is nothing but I am denoting as G, and you have to just calculate the divergence and perform this what is called triple integral. So what is that? Now look, let S denote the positively oriented sphere x square plus y square plus z square is equal to a square, that is okay. And then let G be the solid region that encloses. Now if I have a sphere x square plus y square plus z square is equal to a square, that means the region G which is bounded by this sphere, then you have to just calculate the divergence of F. Now your capital F is given. What is your capital F? This is x comma y comma z, and what is this? This is 0 comma 0 comma z. So this is your vector field. You have to calculate the divergence. What is the divergence of F? That I have already discussed when I talked about divergence, curl, that kind of things. If you see, what is that? This is nothing but if I denote it as a F1, yes. So what is this? So this is, so that means, yeah, okay. So therefore you have to just take the dot product with F, if you remember. What is that? This is del del x comma del del y comma del del z, and what is this? Suppose your capital F is F1, F2, F3, right? So this is F1, F2, F3, and what is that? This is, that means del F1 del x plus del F2 del y plus del F3 del z. That is the one. Okay. So what is that? So you just F1 is 0, F2 is 0, so F3 is z. So that means this is 0, this is 0, so that means del F3 del z. Then what is that? That means this is exactly equal to 1. So therefore divergence of this vector field is 1. So that means you have to calculate. So this is divergence is 1. That means you have to calculate this triple integral. And what is this? This is nothing but the solid region bounded by the spherical surfaces or the sphere with radius a. And what is the volume of this region? This, you know the formula. This is 4 by 3 pi aq, that you know. Right. So because divergence is 1, so you can take out 1. So that means what will remain is the volume of the solid region bounded by the sphere x square plus y square plus z square is equal to x a square. So that means this is a sphere of radius a, and you know the region, solid region bounded by this sphere. What is that? This is 4 by 3 pi aq, that you know. So therefore the corresponding outward flux of my vector field capital F across my sphere x square plus y square plus z square is equal to a square, which is nothing but exactly equal to 4 by 3 pi aq. So that is one example. Another example you can think about, this is example 2. So what I am asking, so I am saying that, okay, let G be the region bounded by the hemisphere. Once again, x square plus y square plus z minus 1 whole square is equal to 3 square, where z runs from 1 up to 4 and the plane z is equal to 1. So therefore you just look at the region bounded by the hemisphere along with the plane. Okay. So this is a solid region. Now what I am asking, I am saying that use the Gauss theorem to find the outward flux of my vector field, this capital F, across the surfaces S of G. That means I have to perform this kind of integration. When I talked about surfaces integral, computing this kind of integral, that means I want to find the outward flux of my vector field capital F across my surfaces S of G. Okay. But to calculate this kind of integral by Gauss divergence theorem, that means you have to calculate the corresponding triple integral over the region G of the divergence. That means you have to just calculate the divergence, and if I calculate the divergence, because my capital F is given, so what is divergence? So that means the capital F has component F1, F2, F3. So what is this? Then you just calculate. That means first one is that del, so then we have to take the derivative of x with respect to x variable. That means this is 1. Second one is del, perform the derivative with respect to y variable, again it will give you 1, and third one will also give. So that means divergence of F is 3. So that is why this is 3, and then you have dV. So that means what we have to do, so you can take outside. So therefore that means 3 times the volume of the hemisphere. That's what it is. So it is you have a hemisphere, right, and then you have the plane. So that means what? So your G region is bounded by the hemisphere x square plus y square plus z minus 1 whole square is equal to 3 square, right? So radius is 3, and z runs from 1 up to 4. So this is the hemisphere, and then you have to have one plane z is equal to 1. And what is the volume of this region? So if that means the volume of the hemisphere, which is nothing but 2 pi. So that means I am talking about the half, that means hemisphere, not the full one. Full one will be 4 by 3 pi aq if a is the radius. So here I am talking about the half. So that means it should be 2 by 3 pi, and aq, a means radius, that means 3. So 3q. So that means it should be 3 times 2 pi 3 to the power q divided by 3, and which is exactly equal to 54 pi. Okay. So, this is the corresponding what is called, if I talk about the outward flux of my vector field capital F across my surfaces, which is nothing but 54 pi if I use my what is called Gauss theorem. But at the same time it says that, look, if I do not want to use what is called my Gauss theorem, then I have to calculate this one surface integral independently. Then what is that? So, if I want to calculate, or if we attempt to compute this kind of surface integral, so that means what is that surfaces? So, surfaces is the upper hemisphere along with the plane z is equal to 1. That means this surface integral I can break up into two parts. One is the upper one and another is the plane z is equal to 1. That means I can break up into two parts. One is the over surface integral, this integral over S1, another over S2. What is my S1? S1 is the hemisphere surfaces x square plus y square plus z minus 1 exactly equal to 3 square, z runs from 1 up to 4, and S2 is the lower one. That means S2 is the circular region x square plus y square lesser equal to 3 square in the plane z is equal to 1. So, that means, so I have a solid region, it is bounded by the hemisphere along with the kind of circular region in the plane z is equal to 1. So, therefore, if I calculate this one independently, different without using what is called Gauss theorem, that means you can break this surface integral of this object f dot, a normal component of my vector field, that you can break up into two parts, S1 and S2. S1 is the upper one, that means S1 is the hemisphere surfaces x square plus y square plus z minus 1 square is equal to 3 square, where z runs from 1 to 4, whereas S2 is the circular region, that means in the plane z is equal to 1. That means S2 is the circular region x square plus y square lesser equal to 3 square in the plane z is equal to 1. So, you have to perform these two integrals separately, and if I add it, then it will give you this what is called surface integral. So, this is another example, you can have it. So, this is another one. Okay. So, maybe I think yeah. So, let me just, maybe I think in my next class I will talk about this example 3. Okay. So, what it says is that, let me just state this example and then maybe in details also. What is that? Okay, let S be the positively oriented surface x square plus, again it is I am talking about what is a sphere of radius 1 with z is positive, and then I say that, okay, compute this object, that means surface integral over my surface S f dot n cap d sigma, where my vector field capital F is given by this one. Then this is very nice actually, you see. So, I have to calculate this object. That means what is my S? S is positively oriented surface x square plus y square plus z square is equal to 1, z is positive. That means I am talking about a surfaces in the kind of z is positive, then positive hemisphere I am talking about, okay. And your capital F is given here. So, now if I want to use what is called Gauss theorem, let us see, let G be the solid region bounded by my surfaces S. So, now this S is what? This S is actually the upper hemisphere. That means x square plus y square plus z square is equal to 1, and then z is positive. Okay. So, now if I want to apply Gauss theorem, I have to start with a solid region bounded by the surfaces. So, that is what I am doing. Let G be the solid region bounded by the surfaces S, that is given, and the kind of region, what is called circular region in the plane z is equal to 0, that means x square plus y square lesser equal to 1. Okay. So, because you see, if I want to apply what is my called Gauss divergence theorem, I have to start with a solid region and then I have to find a surface which encloses my solid region. Okay. So, therefore, the surfaces in the example 3 is given only in the upper half plane, right, that only the upper hemisphere, the sphere. So, but if I want to apply what is called divergence theorem, I have to see a region G, solid region, which is bounded by some closed surfaces, right. What is that closed surface? So, therefore, G is a solid region bounded by surfaces S, which is the upper hemisphere, that means Z is positive, along with the circular region x square plus y square is lesser equal to 1 in the plane Z is equal to 0. Then I can apply what is called my divergence theorem. What is that? That means the region G, which is bounded by the surfaces S along with S1, this surface integral of the normal component of my vector field F, which is exactly equal to the triple integral over the region G of divergence. So, what is that kind of surface integral? That means you have to have surfaces the upper hemisphere along with the circular region S1, that means you have to add it, that means surface integral of this normal component of A plus surface integral over S1. So you have to include both this and this, then they will have the closed surface, and the region bounded by is nothing but G, that is solid region, which is the divergence. Now what is the divergence? You can easily calculate again. So F is very nice vector field, continuously differentiable vector field. What is the divergence? If I calculate the divergence of F, again you have to take the derivative with del F del x, then it will give you 1. Okay. Again del F del y, this is give you 0, and del this is also, so that means divergence is 1. So that means this is nothing but the volume. So 1 will come out, so that means the volume of the region bounded by the upper hemisphere and the circular region. And what is that? I am talking about upper hemisphere, right? So that means it should be not 4 by 3, but it should be 2 by 3 pi AQ. A is the radius. What is my radius is? Radius is 1, so it should be 2 by 3 pi. So therefore this kind of, then I have used Gauss theorem here. So this is exactly equal to this one. No, so therefore, but what is given? The problem there you have to calculate this object. So therefore this object is nothing but 2 pi by 3 minus this object. So therefore the only part is remaining to get the answer of my questions is that you have to calculate this object. That means you have to calculate this surface integral. That means you have to have S1, that means it is in the circular region in the plane Z is equal to 0, x square plus y square is equal to 1. So therefore to compute this object that I want in my questions, which is nothing but by Gauss theorem this minus this. So that means the only part is remaining to calculate this one. But this is also trivial. Why? Because since I am in the region Z is equal to 0 plane, so therefore what is my outward normal? This is a k cap, right? So therefore this is outward normal to the surfaces S1. So what is that? So you just calculate this one. So therefore this integral S1 f dot n cap, which is nothing but, if I calculate vector field F is given, what is my capital F? This is x plus y, z and x square, right? But you have to take the dot product with your n cap, k cap. So that means only the last component will survive. What is the last component? X square. That means, so that means it should be minus of x square. Okay. And this should be what? dA. Okay. So and of course S1 region, you know, it is the circular region in the what is called the plane Z is equal to 0. So therefore you just make it to polar coordinate. If you just calculate it, so therefore it should be, I think, r q cos square theta dr d theta. You just do the performation integral, this is minus pi by 4. Therefore the final, the requirement that you want, which is nothing but this is equal to this minus this, which is 11 by 2 pi. This is the one, right? Yes, perfect, I think. Okay. So I think that is clear. Yes, fine. So therefore the question is that, so you have to just careful what I am asking in my questions, you have to see. So that is why very important. So therefore you should not use, or you should not apply your divergence theorem blindly. Okay. So to apply your divergence theorem, you have to have the solid region and then look at the surfaces bounded, that surfaces which bounded your solid region G. So therefore if you cannot, you should not apply just directly that this is nothing but the by Gauss divergence and this is the one. This is not the case. So because I am asking something which is nothing but the surface integral of the upper hemisphere. Okay. So now to apply the Gauss divergence theorem, you look at the solid region bounded by the upper hemisphere along the circular region in the plane Z is equal to 0. So then only I can apply my Gauss divergence theorem. That means then the corresponding surface integral of this object, that means you have to have the integral over S plus integral over S1. So that is the total surfaces, and that surfaces bounded the region what is called G. And then you apply Gauss divergence theorem. So that means, so this plus this exactly equal to this. That the right hand side you can easily calculate. This is nothing but the region bounded by the upper hemisphere, x square plus y square plus z square is equal to 1, and the circular region in the Z is equal to 0 plane, x square plus y square is equal to 1, which is nothing but 2 pi by 3. So therefore finally the object I want to calculate, which is nothing but the integration or the integral over the surface S, which is nothing but the upper hemisphere, which is nothing but this triple integral minus, sorry, what I have done? Yeah. So this triple integral minus the integral over S1. So the only part is remaining, you have to calculate this object, and this is also okay, not an issue, because since I am in the plane Z is equal to 0, you have outward normal. So this is very straightforward, because S1 is the region, circular region, you have the parametric form x is equal to the circular region 1 radius, and yeah, so that means cosine theta comma sine theta, r from 0 to 1, theta from 0 to 2 pi. If you perform it, this is minus pi by 4. So therefore the required object that I want, which is nothing but this minus this, and this is 11 pi divided by 12. So that is another application, what is called Gauss divergence theorem. So I think I should stop here, because I will explain once again couple of applications again. So, a couple of examples I talked about. So, one more applications I will talk about in my next lecture, and I think that will end the kind of this concept, and I think that I will talk about in my next lecture. So, I think today if I just summarize what I have done today is that, so in my last lecture I talked about Stokes theorem for surfaces, nice surfaces or smooth surfaces. So, today I talked about one example that I was get confused little bit in my last lecture. So, that I started with that one. Then today I introduce another statement of Stokes theorem, that means if I have a surfaces with finitely many holes, okay, then couple of example, one examples I talked about with the smooth nice surfaces, okay, and then I introduce the what is called the statement of Gauss Divergence theorem, and couple of examples I have discussed. So, in my next class I will talk about one more applications of divergence theorem, and that will end this concept. I think today I should stop here. In my next class I will start with the once again recall the statement of divergence theorem, and one applications I will talk. Okay, I think I should stop here. Thank you.